Welcome. In this video, we're going to take a look at the linearity principle and the general first order ordinary differential equation. So our goal at this stage in this lesson is to start thinking about other first order differential equations that maybe aren't separable. We already do know that the first order differential equation, dy dt equals f of ty, and just as a reminder, the reason we know this is first order is because it is the only derivative that is in the function is dy dt, the first derivative. As long as that can be factored into a function of t and a function of y, so if this f of ty can be factored into a g of t and an h of y, where one or both of them are allowed to be constants, then f of ty is separable and can be solved using separation of variables. Nothing super new there. But now we've got to pay attention to the fact that not all ODEs are separable. It's really not difficult to find examples of non-separable ODEs. We'll encounter them not in this lesson. This lesson we're going to focus more on the algebraic structure and focusing on making sense of organizing and structuring differential equations. It's pretty cool and exciting stuff that applies universally, and then eventually we'll get to some modeling. For the sake of our discussion, y is the output variable and t is the input variable. You'll notice in a lot of sources dy dx is used. Y and t are not some special variables, we just happen to use them in our version of this class. For now an ODE will receive three primary classifications. The first one we've already learned about, which is the order of the differential equation. First order means that the highest derivative that's involved is the first derivative. Second order means the highest derivative involved is the second derivative, and so on. So let's just go ahead and quickly classify what we have here. So we have, looks like a second order, and the reason that's a second order is because the highest derivative is the second derivative. Here we see that in this equation, the only derivative that's present is the first derivative, so this is a first order. In this one we see we have the third derivative and the first derivative, but our classification of order is going to be based on the highest derivative present, which is the third derivative, and therefore we call this third order. The next categorization we make is based on whether the equation is linear or nonlinear. And this is really important because nonlinear, just as in algebra, poses some new challenges that often actually in differential equations can't be overcome, and we may not end up being able to solve certain differential equations that are nonlinear. The same can apply to linear in some circumstances, but those are fewer and farther between. So linear is actually kind of confusing because when we see an exponent that's not 1, let's say a half or a third power, we immediately start to think that linearity is not present. But we're actually looking at the order of y. So the exponent of y is what we're interested in, and that's it. It could have a t to the 1000th power in the equation, but as long as y is raised to the first power only, we would consider that equation to be linear. Nonlinear involves y where at least one y in the equation is of order larger than 1. For example, if you saw a y squared, that would be classified as nonlinear. Any function of y, like sine of y, cosine of y, e to the y, those are all nonlinear functions. So you must have a y to the first as one of your terms. Let's take a look at some examples. And the order of t is irrelevant as to whether or not an equation is linear or nonlinear. So this word you just have to be careful about because we mean linear with respect to y. So linear with respect to y. Okay, so if we look at this one, I see a t squared in it, so it's a second order equation, but I do in fact see that y is to the first power, and therefore this guy is linear. I need not look at any other terms except the ones involving the y variable. In this case, I have a first order equation, but y is actually, it's the sine of y, and sine of y is a nonlinear function, so this one would be considered nonlinear. Here it appears that we have y to the first power on first look, but if I rewrite that, I see that y is in the exponent, or sorry, in the denominator, so to bring it to the numerator, I would have to change that 1 exponent to a -1 and write this as -5 times y to the -1 plus 2t equals t squared. And because of this, this is going to be a nonlinear ODE. Here on first sight, I see y to the first and I see a y to the first, but when I distribute this through, I get a y squared. And then I have a y to the first over when I distribute this in. So you have to be able to look at it not in factored form, but in term-by-term form where everything is expanded. And I see that because of this term here, this is a nonlinear ODE. Even though it has a y to the first, remember, quadratics are always going to trump linear terms. Here's another one. Now, by the way, when you start getting into higher orders, it's sometimes just convenient, right? We wouldn't want to write y 1, 2, 3, 4. That's just too many primes on it. So we often avoid that notation. Another way of writing y, this is the fourth derivative of y. So you could write it like this as well. But again, I just want to get you used to working with y primes because it's a little bit easier to write down and you don't have so much notation. So that just means the fourth derivative. Notice that it's in parentheses. If it were just y, this would mean y to the fourth power. But as long as you put parentheses around that, that means the fourth derivative of y. Okay, so I look at the y term, which I see here. Now that has a sine of t, but it's multiplied by y to the first power. So coefficients that involve t or constants do not affect the order of y. It's still something times y to the first power, and so this would be considered linear. The third classification, which often I think most people think is weird at first, is the distinction between homogeneous and non-homogeneous. So this is just in terms of whether or not there is a standalone function of t. So here I've just given kind of an example of a full-blown second-order differential equation that's linear. Notice that it's linear, it's the first power here, y to the first. And then I just have these coefficients that are some functions. So they could be constants, they could not be constants. It doesn't really matter. These are just some functions involving t. So this could just be the second derivative plus 1 dy dt plus 1y. And so in that case, f1, f2, f3 could all be constants. So remember, functions can be constants, but functions can be constant functions. But functions involving a different variable other than t would not be categorized as an f of t. So if, in order for this equation to be homogeneous, we notice that this is a standalone function of t. And all we mean by that is that if all of these other functions of t are attached as coefficients to a function involving y. So second derivative of y, first derivative of y, y to the first power. So anything that's left over, if you move all the terms involving y to the left, is an easy way to do this. And then the only thing that you leave on the right-hand side is anything that doesn't involve y. If that standalone piece right there is not 0, then it's considered non-homogeneous. If that thing were equal to 0, if all you had left on the right-hand side was 0, then it would be classified as homogeneous. So just think about it this way. If that were a 0, it would make life a lot easier. And homogeneous makes things easier, non-homogeneous things, and it makes things a little bit more complex. Not impossible, not difficult, but just more involved. Now, one thing that we should notice is that if you do have a homogeneous equation, then y equals 0 is a solution. So like if you look at this, dy dt plus y equals 0. Well, if y is 0, then the derivative of y is 0. So you would get 0, and if y is 0, that would be 0. 0 plus 0 is in fact 0. So that solution will always work for homogeneous ODEs. It's called the trivial solution. I just wanted to get that out there. Trivial just means that oftentimes if you took a wild guess, 0 would be the thing you take a wild guess at. It's like trivia. Okay, non-homogeneous simply means there is a term that is solely a function of t in the above form. That is, f4 of t is not the 0 function. So basically, as I mentioned earlier, if you get all of anything involving y to the left and keep everything else not involving y on the right, then you can really easily tell if it's homogeneous or not. So here I have both terms involve y on the left. The only thing that's left over on the right that is 0, and so because of that, this is a homogeneous equation. Now in this one, if I look at this, first of all, so I see that there's a function of y on the left. There's another function of y on the left. But wait a minute, I've got this plus 2t here. That doesn't belong on the left. On the left, we only want to keep functions of y. So we have this second order nonlinear equation. And if I move that over, I now see that what's on the left is not equal to 0. And therefore, this equation is non-homogeneous. So you might need to rewrite it a little in order to see this. Now here I've just written it differently. Instead of y prime prime, I've just to get you comfortable with the notation, we have t squared times the third derivative of y minus 2 times the second derivative of y with respect to t plus 1 equals 0. So this would be considered a linear equation because, first of all, there is no term involving y. And so the highest derivative is 3, therefore this would be third order. Is it homogeneous? Well, anything that doesn't involve y, I want to move to the left. So I'm going to subtract away this 1, and now I have t squared times the third derivative minus 2 times the second derivative equals negative 1. And because this function of t here, I know it's a constant, but it's still a function of t, makes this equation non-homogeneous. Almost there. So that's all of our classifications, and you could say that an equation is, for example, first order homogeneous linear, or you could say that something is second order nonlinear non-homogeneous. So these classifications will often tell us what methods we have available to us. Now, one thing that we will note is that non-homogeneous ODEs are often a little bit more complex to solve. And as it turns out, all of the equations we've solved so far using separation of variables have been, by default, homogeneous. And the reason for this is that recall that when we write equations of the separable form, they can be factored into two pieces. And when they can be factored, that means there is 0 residual. And I'm going to use the term residual often. Residual just means the stuff that's left over. And because there is 0 residual, you can see here that I can rewrite this equation as dy dt minus g of t times h of y equals 0. And because the only thing on the right-hand side, after all the y terms have been moved over, this is, for this reason called homogeneous. Now the specific case that we're looking at is the first order linear differential equation, which we're going to define down here. So the first order linear differential equation, when we see that nomenclature, what we should be thinking is, okay, it has the first derivative as the highest derivative. It's a linear function, so it's y to the first power, and it's a differential equation. Now notice we haven't specified homogeneous versus non-homogeneous here. And the reason we haven't specified that is by default, we're just going to study every equation that has this form. So dy dt equals a of ty plus b of t. Now I want to just draw your attention to a comparison here. It's not the exact same thing, but the linear equation y equals mx plus b. When we studied that in algebra, the reason we called this linear is because y and x were both to the first power, but in our differential equation, y is actually y prime and x is actually y, and m and b are these m is kind of like, well, it would be a slope. It's not really a slope here, but it acts as kind of that same coefficient as m does in the linear algebraic equation. And b of t is kind of very similar to b. So when you look at this, it looks kind of like a linear function if you can imagine that a of t and b of t are just sort of like m and b. Now, a of t and b of t don't have to be constants. They could be functions of time. But needless to say, it has the linear structure, and this y to the first power really declares that. So we often just call these folds or FOLDEs because these labels can start to get kind of long, like second order, homogeneous constant coefficient linear differential equation is a lot to say every time. Now this equation right here, we said that we were not going to make the distinction between homogeneous and non-homogeneous in the nomenclature, but we can study the homogeneous version of this equation, and that will be when b of t is equal to 0. That's the standalone function that would be left if we moved all the y's to the left-hand side. So now this equation would look like this. dy dt equals a of t times y plus 0. And if you study this for a moment, you see that this is what we've originally referred to as g of t, and this is what we've originally referred to as h of y. It involves a product, and so if you make a first-order linear differential equation homogeneous, it becomes separable. Now, in order to study the non-homogeneous differential equation and learn how to solve it, we need a couple of theorems here. So we're going to introduce our first theorems of the semester. If y sub h of t, we're just using that subscript of h to distinguish it from another function. So the sub h has very little importance at the moment. But if yh is a solution to a homogeneous ODE, that's homogeneous, that's why we use the h there, then so is any constant multiple of the solution, k times y sub h of t, where k is just any real number. And typically and ideally, that's going to be a non-zero real number. So it could be a fraction, decimal, but the second you put a 0 out there, it becomes a pretty boring solution. You get the trivial solution. So first of all, let's show that y sub h of t is a solution of dy dt equals y. Then show that any multiple of that is also a solution. So if y sub h of t is e to the t, in order to verify that it's a solution, I've got to check, does its derivative equal itself? And so if I take the derivative, y prime of h of t, y sub h, then I get, well, the derivative of e to the t is e to the t. Now when I substitute in the derivative of that solution, which is e to the t, and I substitute in the function, which is e to the t, are they equal? Yes, they are. Therefore, e to the t is a solution. Now again, the y sub h is just used to denote that it's a solution to a homogeneous differential equation. So don't let that throw you off. That's just, soon we'll see that it doesn't have to be a solution to a homogeneous case. And show also that k times y sub h of t is also a solution. So if y sub h of t is e to the t, then if we multiply that by k, then k y sub h is k e to the t. So the derivative of that, the derivative of k times y sub h, the prime of that is the derivative of this function, which is simply equal to, well, the derivative of k e to the t is k e to the t. The coefficient out front doesn't make a difference, and now we just need to check, does dy dt equal the original function? Well, they are the same, right? So if I plug in k e to the t for the derivative of that, and the function that I took the derivative of was also k e to the t, they are in fact equal to each other. So once again, I've just shown that since this is a solution, so is any multiple of that solution. Now let's just do a general proof here, because we've verified it for one specific differential equation, but I don't want you to be afraid of convincing yourself that something is mathematically true. And how do you verify something? So the theorem says that as long as you know, the condition is that y sub h is a solution to a homogeneous ODE. So what we're going to need to verify is, first of all, let's focus on the first order linear differential equation. So first of all, we'll say something like this. Well, the condition is that you found a solution, right? So first of all, suppose y sub h is a solution to dy dt equals a of t times y. So that's the first order linear differential equation. Notice that I have a plus 0 here. That's my homogeneous case of this equation. And so as long as this equation is homogeneous, this means that if I were to take the derivative of y sub h, that would in fact equal a of t times y sub h. So that's what that means. So all I've done here in practice is I've used the condition from the first step, which basically said that suppose it is a solution. Well, if it is a solution, that means I should be able to plug in its derivative on the left, the function on the right, and I should get the two sides to be equal to each other. So this is a true equality here. So if that's the case, let's now check or construct the solution, or construct equality for k sub h, or k times y sub h. So if all I were to do here is the derivative of k y sub h, the derivative of that with respect to t, right? Now this is literally another way you could write dy dt is it's the derivative of this function with respect to t. So if I have the derivative of a constant multiple of something, that means I can factor it out. So k times the derivative with respect to t of y sub h. Okay? And now I know that the derivative of y sub h with respect to t, I know that this whole thing by equality is equal to this whole thing. So this leaves me with k times a of t times y sub h. Now, because I have the multiplication of three things here, I can rearrange the order in which I multiply those things. And if I write it like this, you can in fact see that from our equalities here, from our three equalities, what we're now able to deduce is that the two ends are equal to each other, right? Because I have a bunch of equal signs here, and so ultimately, since these things are all equal, it follows that the derivative of k times y sub h is equal to a of t times k times y sub h. And so notice that this and this are identical, and that basically this k times y sub h satisfies the differential equation. So if in our equation I had replaced y sub h with k times y sub h, the equality still works out. And for that reason, this multiple of y sub h is also a solution. Now, this linearity principle has an extension, and that extension says, given the non-homogeneous ODE, dy dt equals a of ty plus b of t, and its associated homogeneous reduction. So even though the equation that you have may not be homogeneous, if you omitted that b of t term and just left it as plus 0, if you literally reduced it down to deleting that, and you found a homogeneous solution, y sub h, as the general solution to the homogeneous reduction equation, and you found some particular solution to the non-homogeneous equation, then the general solution is we could take those two solutions and add them together, and that would form the general solution to the non-homogeneous case. Now that doesn't seem like it helped us at all, because even though we know how to solve the homogeneous equation by using separation of variables, to find this particular solution to the non-homogeneous case seems like it just puts us back at the start, but we've already done a lot of work. Before we get into how we would actually find y sub p, that's the thing that we're going to be after, let's just go ahead and see that this theorem actually works. So show that y sub h and y sub p are solutions of the homogeneous reduction and non-homogeneous equation dy dt equals negative 4y plus 3e to the negative t. So the homogeneous reduction of that would just say omit the 3e to the negative t term. Here's my a of t, here's my y. So let's just focus on this equation right here. Now I just need to check that y sub h, this guy here, I just need to check that that satisfies this equation. So I need to make sure that the derivative of this guy, that the y prime of h, okay, so that's going to be, the derivative of that will be negative 4k e to the negative 4t. Y sub h, of course, is just k e to the negative 4t. And if I now plug those two equations in, or those two functions in, for the left and for the right, the derivative, negative 4k e to the negative 4t, I want to see, does that equal negative 4 times y? Well, y is k e to the negative 4t. And if I just remove the parentheses, you see that, in fact, these two sides are equal, and therefore y sub h is a solution to the homogeneous reduction. Now we want to show that y sub p of t is a solution to the non-homogeneous case. So now I just want to check, does y sub p satisfy this equation right here? And in order to do that, I have to look at y sub p. So y sub p is the equation e to the negative t. Its derivative is negative e to the negative t. And now what I need to do is just plug in y prime up here, plug in y sub p in here, and see if the two sides are equal. So does negative e to the negative t, question mark, equal negative 4 times e to the negative t plus 3 times e to the negative t? So on the left I see that I have, or on the right I see I have negative 4 e to the negative t plus 3 copies of e to the negative t. That actually gives me negative 1 copies of e to the negative t. And the left-hand side, there's nothing to reduce, but I do see that they're equal to each other. Finally, it says, show that the sum of these is also a solution. So in order to do that, what I'm going to have to do is I'm going to have to now look at the general solution, which is y equals the sum of the two functions. So the homogeneous is k e to the negative 4t. If I add to that the non-homogeneous, the y sub p, which is e to the negative t, I want to check, is this a solution of dy dt equals negative 4y plus 3e to the negative t? Okay, so what I'm going to do to verify this is, first of all, I need the derivative of this guy. So the derivative of what I'm claiming to be the general solution is negative 4k e to the negative 4t. And then the derivative of e to the negative t is negative e to the negative t. And now if I come over here and I plug in y prime for dy dt, and I plug in y for negative 4y, then on the left-hand side, I will have negative 4k e to the negative 4t minus e to the negative t. So I've just replaced dy dt with the derivative of y. And now I want to check, is that equal to negative 4 times the y function, which is k e to the negative 4t plus e to the negative t, and then add on the end of it the result. So this piece here is just our substitution for y, plus 3e to the negative t. So first of all, I'm going to see that when I distribute this, here I'll get negative 4k e to the negative 4t. Now when I distribute it here, I'll get negative 4e to the negative t, but then I'm going to be adding positive 3e to the negative t to it, so this will leave me with negative e to the negative t, and check it out. The two sides are, in fact, equal to each other. Therefore, I have proven that the particular solution, which is e to the negative t to the non-homogeneous case, added to the solution for the homogeneous reduction forms a solution that's general for the entire differential equation. Let's see that this works. So suppose that y sub h of t is a solution to the homogeneous reduction and that y sub p of t is a solution to the non-homogeneous case. So we start off the proof by saying that. So if that's true, then I want to check is y equals y sub h plus y sub p, is that a solution? Well, if I want to verify that it's a solution to this non-homogeneous case, then I'm going to need its derivative as well. And the best I can do is I can just write this as y prime of h, or I could write, so I can write y prime sub h plus y prime sub p. Now, since we don't know what functions they are, all we can say is that, well, the derivative of y sub h is y prime of h. The derivative of y sub p is y prime of p. And so now, if I want to verify that it's a solution to dy dt equals a of ty plus b of t, what I need to do is show that the two sides are equal to each other. So the derivative of y, that's going to be y prime of h, or I'm going to write it as dy h dt, and y prime of p I'll write as dyp dt. And does that question mark equal a of t times y? Well, y is y sub h plus y sub p, and then plus my b of t term here. Now, this becomes sort of an algebraic argument. When I distribute this, I'll have a of ty sub h plus a of t y sub p plus b of t. And I want to see if these two sides are equal, but there's not much algebra to go off of here. The only thing that I'm allowed to use is the fact that I know from the suppose that y sub h is a solution to this. So notice that what I have here is y sub h, the derivative of y sub h. Well, what I know that that's equal to is a of t times y sub h, because I know that y sub h is a solution to that homogeneous reduction. I also know that y sub p, its derivative, better be equal to a of t y sub p plus b of t. So the green is equal to the green, the purple is equal to the purple, and therefore these two sides are equal to each other, because the green plus the purple equals the green plus the purple, for a lack of mathematical speak. All right, so there's kind of some algebraic proofery, so for a lack of better terms, some mathematical proof for why this theorem works. So a lot of times when we're proving something, we're using general arguments. We're trying to show that things are equal to each other, and we have to do so with limited knowledge about what those functions might be. Of course, we can prove it for specific examples, but theorems aren't very good if they are just for specific examples. We need them to be good for any function that we deal with. Okay, so for example 2, we had the equation dy dt equals negative 4y plus e to the negative t. That was the equation that we wanted to solve. Now the process in doing this is to first of all find y sub h. Okay, so that we can derive by doing the homogeneous reduction. And the homogeneous reduction of this equation is going to be dy dt equals negative 4y. So we made it homogeneous. Now, of course, again, this is not the original equation we're set out to solve, but the theorem, the extended linearity principle, tells us that if we go through this process, that we will find the general solution. So by separation of variables, if I divide, if I see the two factors here are negative 4 and y, so I'll divide the y over and leave this as negative 4. I'll integrate both sides with respect to t. And so that leaves me with the natural log of y equals negative 4t plus c. And now if I exponentiate, I'll get y equals e to the negative 4t plus c, which we could use the properties of exponents to break up like that. So that right there is what we're calling y sub h. So I suppose along the way we should have just written y sub h everywhere to indicate that what we're solving for is for y sub h. But we could do it on the back end here too and just say, define this thing to be called y sub h. So notice that matches what we had as the, confirm that k e to the negative 4t is the homogeneous solution. And notice that any multiple of e to the negative 4t is a solution. So step 2, find any one solution, any non-trivial y sub p of t. And this is where things can get a little bit interesting. So in order to do that, I have to consider the whole equation. And what I'm going to do is I'm going to write the equation like this. I've just moved the 4y to the left and left the non-homogeneous piece by itself on the right. The reason I write it like this is because this will help me take a good guess at what y sub p should be. It basically says, if I read this as an English sentence, that the derivative of the function plus 4 times the original function has to equal 3 times an exponential. Well, the only function that when I add these two things together that will end up being exponential, and the only function, in fact, when you take its derivative that will be exponential, will be some function of the form. Our guess will be that y sub p has to be some multiple of e to the negative t. All right, so the reason I'm saying some multiple is that it may not just be e to the negative t, but it's going to be some function of e to the negative t. And if I use this as my guess, then that implies that the derivative of that guess will be negative a e to the negative t. Okay, so what I'm going to set out to do here is I'm going to try to find that value of a to make this all work out. So if I plug in the derivative up here, and I plug in the y function here, that will say that negative a e to the negative t plus 4 times y, which is a e to the negative t, has to equal 3e to the negative t. When I combine these two terms here, I'm going to say, well, I have negative a multiples of e to the negative t. I have 4a more multiples of e to the negative t. Well, when we combine like terms, we add the coefficients. So this will be 3a e to the negative t has to equal 3e to the negative t. Now we see that they look similar, but I have this unknown thing floating around here called a. And the only way for these two things to be equal to each other is for their coefficients to be the same, right? So the coefficient of the e to the negative t on the left is 3a. The coefficient of e to the negative t on the right is 3. So it must be the case that 3a equals 3, and that tells us that a is equal to 1. So y sub p, our particular solution that works for this guy, is going to be 1e to the negative t. And notice that that is exactly the same thing that we had been given up here, is that the particular solution is e to the negative t. Now the reason we call this a particular solution is that it has no arbitrary constant, that the only value of the arbitrary constant that will make this work out is if a is equal to positive 1. So that's why we call it a particular solution, because that arbitrary constant has to be 1 for this to work out. Now you can see why my guess here was of the form e to the negative t. If I had picked something like e to the negative 2t, then I would have had an e to the negative 2t on the left, and I would have had an e to the negative 1t on the right, and those two functions will only sometimes be equal to each other when they intersect. Now my general solution, the last step of this, is to say that y is going to equal the homogeneous solution plus the particular solution. The homogeneous solution was k e to the negative 4t, and the particular solution is e to the negative t, and I'm done. What we did here to solve for that non-homogeneous solution, y sub p, we use what's called the method of undetermined coefficients. That is, we knew that our particular solution had to involve the function e to the negative t, so that we ended up with e to the negative t's on both sides. I just didn't know what that coefficient was. That was undetermined, so this method is called the method of undetermined coefficients. Let's look at another example. Find the general solution of this guy here, which notice again has that form dy dt equals a of t times y plus b of t. So a of t is going to be the coefficient of y. B of t is going to be negative 4t. And I'm going to put a plus sign between them because I see that in order for these two things to match, for the template to match the function, it's got to be a plus something. So my b of t is actually negative 4t. So step one, find y sub p. I'm sorry, y sub h. You could find y sub p first. There's not a specific reason why we solve y sub h, just because we're used to it. So what we need to do is we need to solve this differential equation. Now, as above, I'm not going to put y sub h here. We're just going to call the result y sub h to this differential equation. I just don't want to have to keep copying down y sub h. So I'm going to divide by y. You can see that by now that this is going to work out to be k e to the 0.2t. But if I now integrate with respect to t on both sides, I'll get natural log of y equals 0.2t plus c. When I exponentiate both sides, I'll end up with k e to the 0.2t. All right, that's what we're going to call y sub h. So I found my homogeneous solution. Step two, find y sub p with the method of undetermined coefficients. And so here is my equation. Again, I'm going to move the y term over. You don't have to do that. You could leave it as is, but I'm going to leave the negative 4t here. Now this one's a little bit different because when I read this, I see that if I take the derivative of my solution and I subtract away 20% of that solution, I should end up with a linear function, negative 4t. But the problem is that if I take y to be a linear function, its derivative is a constant function. So what I will do is, I know that if I take the derivative of a linear function, if I call y sub p, if I say it's going to be some sort of linear function, a, maybe I don't want to use a here because I'm kind of using a of t up here. Let me write this as some constant times t plus some other constant. And the reason I have to do that is because once I take the derivative of this, I am going to end up having a linear function. I'm sorry, we don't really need the d on there because that's not going to influence our derivative. But if I take the derivative of yp, I'm just going to get the constant c. So now, if this is in fact my guess, right, I'm just guessing that the solution is going to look something like this, then I better be able to find the value of c that makes this equation true. So I'm going to again plug in the derivative here. I'm going to plug in the function here. And so c minus 0.2 times ct has to equal negative 4t. And I need to find the value of c that's going to make this equation true. So if I do the subtraction on these, which the best that I can do here is factor out a c and make this 1 minus 0.2t equals negative 4t, or better yet, let's write it like this. Let's write it like this. Let's say that we leave this as negative 0.2 ct plus c has to equal negative 4t. So in order for these two equations to be equal, this coefficient of t has to equal the coefficient of t on the right. But in order for the two sides to be completely equal, then it would have to be the case that the only thing that I have left on the right is a plus 0. It would have to be true that c is equal to 0 in order for the purple pieces to be equal to each other. But that's a problem, because if c is equal to 0, then this whole coefficient here in green will be 0, and that will not allow me to get that to be equal to -4. So one way around this is to say, well, I kind of need another dial to be able to turn here. And the trick to problems like this is that if you know your solution, your function needs to be linear, then start off with a full-blown linear equation. So make this ct plus d. The derivative of ct plus d will still be c, but what advantage this gives me is that now, in the substitution for y, I'm going to erase this stuff here and kind of go back to the drawing board, is that now the left-hand side in the parentheses will be ct plus d, and that has to equal -4t. So watch what happens. If we distribute things through, we'll have c minus 0.2 ct minus 0.2 d has to equal -4t. Now I see that I have that t term here, so I'm going to write this as -0.2 ct, and then I have left over c minus 0.2 d. And that has to equal -4t plus 0. And the reason I write it out like this is because this coefficient here has to equal this coefficient there. That's the only way that the t terms can be equal. Also, I know that c and d are just some constants, so c minus 0.2d is also a constant. And that constant has to equal 0. So basically what this gives me is a system of equations to solve where I must, so system of equations that must be true is -0.2c has to equal -4, and it must also be the case that c minus 0.2d equals 0. Now this equation allows me to solve for c right away. So if I divide both sides by -0.2, I will get 20 as the value of c. And now what I can do is substitute in 20 for c here and make this 20 minus 0.2d equals 0. And now I can solve for d, and I get d is equal to 100. Great, so as long as c is equal to 20 and d is equal to 100, these two sides will be equal to each other, and so my y particular should be 20t plus 100. Okay, so my y particular, so therefore my y particular is going to equal 20t plus 100. And you can just double check that we solved for the correct term. If I put in 100 up here for dy dt minus 0.2 times 20t plus 100, and you distribute that through, -0.2 times 20 is going to be -4, so that'll give me the -4t. -0.2, I'm sorry, this shouldn't be 100. This right here will be our 20, because that's our value of c. -0.2 times 100 is -20. -20 plus 20 is 0, and so then I'll just have -4t on the left, -4t on the right, and so they are in fact equal to each other. What we did here again is the method of undetermined coefficients. We started off with a guess that wasn't quite right because we left off this plus this constant term. But when we put that constant term on there, what it did is it allowed us to balance the equation and that value of d allowed us to ensure that c didn't have to be 0 like it did when our guess originally involved the lack of that plus d. So another key advantage here is that if you see that you want your right-hand side to equal a linear function, then your y particular should be the full-blown form of a linear function. If this here was quadratic, then this should be a full-blown quadratic. If this were cubic, this should be a full-blown cubic. All right, one more example, and then we'll call it quits. Here is a differential equation where the non-homogeneous piece involves a sinusoidal function. I'm giving you the hint here because a lot of times this is guess and check. But this one's kind of a trickier one because it actually needs to involve both the sine and the cosine, even though this only involves sine. And I'll show you why here in just a moment. So step one. Oh, and lastly, one thing we forgot here is that the general solution is the sum of the homogeneous and the particular. The homogeneous piece we found to be k e to the 0.2t. The y particular is 20t plus 100, and therefore our solution is this guy here, y equals that. And now if we had, for our differential equation, if we had an initial condition, we could solve for this value of k just like we have before. So here we'll go ahead and solve for y sub h. And to do that, again, we're just going to do the homogeneous reduction, 0.2y. Now we already know how to solve that. That's going to be the same thing. That's exactly the same equation we had to solve in the last problem for the homogeneous reduction. This is going to be k e to the 0.2t. That's typically the easier part. Now we need to solve for y sub p. In order to do that, what we need to, we said that we're going to use this as a template. Now the reason we're going to use that as a template, and again I'm just going to subtract over and leave the non-homogeneous piece on the right by itself. The reason it needs to involve sine and cosine, if I had just used sine of 2t, then this guy here would have been sine of 2t, but we have to take the derivative of sine, and the derivative of sine is cosine. It would be 2 cosine of 2t. And the problem here lies in the fact that I would have to add or take the difference between a cosine and a sine, and that's not going to leave me with a sine. The trick to dealing with that is that if you have both the sine function and the cosine function, then the derivative of y sub p will involve both a cosine and a sine function, and that will allow things to cancel out quite nicely. So let's say that we're just going to take the advice here, and we're going to set y sub p to be a sine of 2t plus b cosine of 2t. Now notice that we're taking cosine of 2t because that's part of our argument in the sine function. If we did sine of 3t, then that wouldn't work because sine of 3t can't equal sine of 2t. They have different frequencies. So the derivative of this will be, well, the derivative of sine 2t is 2a cosine 2t. And the derivative of cosine 2t is going to be negative 2b sine of 2t. All right, so now what I need to do is just go ahead and plug things in. So I'm going to plug in, that's the prime of y. Plug that in for dy dt. Plug in y sub p for y, and figure out what value of a and b will make these two sides equal. So it looks like a big messy thing, and kind of is at first, but now I'm going to plug in my derivative for dy dt. And then for y, I'm going to plug in y sub p, so minus 0.2 times a sine 2t plus b cosine 2t, and I need that to equal 3 sine of 2t. So obviously I want the cosines to go away, but notice that there will be an opportunity to cancel the cosines. If I do some distributive property here, then one thing that I'll notice is that I'll use a different color here. The term that I get here added to the term here, I want those to cancel out and give me 0. But I want these two pieces that I get from here and here to give me a coefficient of 3. So let me rewrite this a little bit more. So I'm going to get all my signs over here. So I'll have negative 2b sine of 2t. Then when I distribute this, I'll have negative 0.2a sine of 2t. And now I'll have my cosine pieces. So I'll have plus 2a cosine of 2t minus 0.2b cosine of 2t. And that has to equal 3 sine of 2t. Not sure what happened there. 3 sine of 2t. Okay, great. So now that I have that, I am now ready to make some equalities here. So first of all, from these two terms, I see that I have negative 2b sine 2t's, and then negative 0.2a more sine of 2t. So if you want to perceive it as factoring out a sine of 2t, I will have negative 2b minus 0.2a. That's going to be the coefficient after I factor out a sine of 2t from those terms. Here I'm going to factor out a cosine 2t, which will leave me with 2a minus 0.2b cosine of 2t has to equal 3 sine of 2t. And I'm just going to write on the end of this, I'm going to write plus 0 cosine 2t. And the reason I'm going to write that is because now I can equate the coefficients. I know that the coefficient of sine has to equal the coefficient of sine. I also know that the coefficient of cosine has to equal the coefficient of cosine. So this gives me two equations. This gives me negative 2b minus 0.2a equals 3. And it also gives me another equation, 2a minus 0.2b has to equal 0. So I have a system of two equations and two variables. You can do something like substitution. You can do something like elimination. You can do something like matrix reduction to solve this. You can do this graphically to figure out what A and B need to be. But this is just a system of linear equations. I'll show you how to do it real quickly in Wolfram Alpha. So to solve a system of linear equations in Wolfram Alpha, it's just a matter of putting the two equations in. Notice here I have them separated by a comma. And the input interpretation uses these squiggly brackets, and what that actually means is the input is the set consisting of two equations, and when Wolfram Alpha sees this, it automatically knows, oh, I'm trying to find the value of A and B that will simultaneously make both of these equations true. If you think about A and B as X and Y, it's really, this is the A axis and the B axis, it's where these two lines intersect, and they intersect at the point when A is about negative 0.15 and B is about 1.49. So that's the values that we would get. You can see it'd be incredibly hard to guess these. So we don't want to guess these. We want to try to come up with them systematically. And this way of doing it is very systematic. And so that means that my y particular, which is a sine bt, which is negative 0.15 sine of 2t, minus 1.49 cosine of 2t. That's my particular solution. So going back here, remember we set off to find the values of a and b to make this particular solution satisfy the equation. And finally, what we need to do is just add together to get the general solution, the homogeneous, and the particular. Now, you could just say that this is the solution, but if this is just one particular solution to it, I don't have any arbitrary constants, so I'm not going to be able to get the the particular solution by itself to satisfy any initial conditions other than the one that it already satisfies. So I want to add together these two solutions, which are k e to the 0.2t, plus my homogeneous, which is negative 0.15 sine 2t minus 1.49 cosine of 2t. Now, just as a final word, the guesses that you make for the particular, two key things here to remember. Always look at the structure of the equation. If the homogeneous piece is a linear, then your guess is going to need to be a linear. If the non-homogeneous piece is an exponential, then your guess is going to be some multiple of that same exponential. If your function, your non-homogeneous piece, is a sinusoidal, whether it's sine or cosine, then your particular should be the a sine whatever times t plus b cosine whatever times t. Doesn't matter whether this is sine or cosine, the particular case for a sinusoidal needs to be the sum of those for the reasons we've described.